Hello and welcome to the last subunit in the Verilog2 notes. We've been through the complete synthesizable subset of Verilog and illustrated it with a wide variety of examples of valid use of such. Now what we have to do is start building up to doing larger designs, and we're going to start doing that here with a sample problem that's still relatively modest in scale. This problem is to build a checksum unit. What a checksum unit is used for is to test if a packet is properly transmitted. And the way that is done is that you accumulate a value. You send 8-byte packets as the 8-byte contents and an additional checksum. So this is the payload up to FF, and this is a checksum sent with it. The idea is that you add the payloads together as they come in, dropping the high order bits, and you compare that with the checksum. So here's two examples. Again, we've got a 9-byte packet, 8 bytes payload, 1 byte checksum. In this example, 1 plus 1 plus 1 plus 1 plus 1 minus 1 is 6. The checksum sent with the packet is also 6. We compare that against the calculated checksum for the first 8 bytes. There's no error in this case. In contrast, here we have a packet. Actually, this packet has 2 errors in it. If it was intended to be the previous packet. But if you add up everything up to the checksum in this packet, you would expect to have 7. The calculated checksum is 5. So now we have an error, and we want to report such. The idea being that if you detect such an error, you ask for the packet to be retransmitted. So what I want to do is design a checksum unit that performs this functionality. Its inputs are a control signal, new packet, that goes high when a new packet starts, and data in, which is this 9-byte structure, coming in sequence 1 byte per clock cycle. The output is error. I want that to go high and stay high if an error occurs, and only go low when a new packet starts. So down the bottom here, I've illustrated a sample timing diagram showing what I expect. New packet goes high. The first byte arrives on the next clock cycle. 8 bytes later, we've finished the payload of the packet. We calculate the checksum and compare it with the transmitted checksum. In this case, there's an error, so the error flag goes high in the next clock cycle and stay high until new packet is asserted again, in this case straight away. The first thing to do is to think about the strategy you're going to use in order to do this. And very explicitly, it's not a for loop. What we're going to do is implement a counter to count through the bytes of the packet from 0 to 8 for each of the 9 bytes in the packet. And on the 9th byte, compare the calculated checksum, which is going to come out of an accumulator, which we've seen before, with the checksum that was sent with the packet. So this is illustrated at the bottom here. I'm going to have a counter and I'm going to have an accumulator. The counter is set to 0 on when new packet is high, as is the accumulator. As I count through the packets, the accumulator keeps adding the data in to the current value of the accumulator. When the count reaches 8, I'm calculating the total calculated checksum. I compare that with the transmitted checksum. If they're different, I send the error flag high. If they're not, I keep the error flag low. So let's talk about the steps of the design. And remember, I'm going to sketch a design here before coding it. The first step, which is what we already went through, is to identify a strategy for performing the intended logic function. Again, we're going to use an counter to control an accumulator and to decide when to do the comparison. We next draw the I/O. So here are the I/O for this particular example. A new packet, a control signal, the input data in, which contains the packet, sent one byte per cycle, and the error flag. We then decide what has to be in registers. And remember, the decision as to what has to be in the register depends on what data values have to be preserved across clock cycles or across multiple clock cycles. Well, we can see what needs to be preserved from the specification from the sample timing diagram. Obviously, we need a register for the counter. We also need a register for the accumulator because we want to know the previous value of the accumulator total at the beginning of each clock cycle. We also need a register for the error because when error goes high, we want it to stay high until a new packet comes along. So that defines what registers we need. So we've identified the registers, and they are as follows there: error, count, and accum. We then describe the combinational logic, and here we can be a little loose. I tend to be a little loose and keep certain details in my head rather than carrying every detail going forward here. So here's the combinational logic. And in every case is consisted of a multiplexer in front of the register with multiple alternative inputs controlled by external and internal control signals. So let's look at count. There are two inputs to this multiplexer, 0 and count plus 1. If new packet is high, we want to select 0. If count is less than or equal to 9, as we'll work out in a moment, then we want to keep counting. If count is, then we have the accumulator. Again, if new packet is high, we want to be 0. Otherwise, we want to add data in to the current value of accum. We want to keep doing that until count reaches 7, because that's the end of the packet. Error. When count equals 8, we want to compare data in to the output of the accumulator. And when new packet goes high, we want to set error to 0. This idea of putting a multiplexer in front of all your registers and defining the alternative inputs, then defining how those are going to be selected, is a very useful way to approach the next step of design for any design. We should, in addition, sketch a timing diagram to verify that this runs correctly as per the previous page. And remind you here, the controller is a counter. We're talking about separate control from data path in a later module. We then translate this design into code. And here is that translation. I've lumped all the flip-flops into one procedural block. Of course, by using non-blocking assignment, this is quite safe to do. So what I'm doing here, if new packet is high, I'm clearing all my registers. Else I'm using count to decide when to take the bottom or other input to these registers. If count is less than or equal to 7, I keep accumulating. When count is equal to 8, I set the error flag, and I do that by seeing if accum is equivalent to data in. Remember, this is a logical operator producing a 1-bit result. I set the error flag to the inverse of that, because if they're identical, then that's okay. I keep counting while count is less than or equal to 8. that means count will stop at 9. And this is quite important, though less explicit up here, because I want to make sure that my error flag stays high, but I don't want to do this comparison again and again and again. If I stop the count at 8, I'd be doing this comparison again and again and again, which would actually lead to a logic error. Well, that ends this particular module where we went through the entire synthesizable subset of Verilog. I hope this module was useful to you. It's a very substantive module. It allows you to start building up the tool set to enable you to actually start producing useful designs. What we're going to do next is look at building the tool set up even further in terms of how to approach doing larger designs. We'll look at finite state machines and then look at how to manage complex designs. Thank you very much. I will talk to you in the next unit.